Okay, so we can see that we can use probability to classify instances. So we can classify instances, instances in this case are the people, and we can classify them as preferring dark chocolate, milk chocolate, white chocolate, or none. And we have developed, we can say, a probabilistic model for doing this. Okay, so let's just quickly review some terminology here. So when we have a data set, we could refer to the input variables as the independent variables and the output variable as the dependent variable, or we could refer to them as the input variables and the output variable, or in statistics they call these the explanatory variables versus the response variable. So there's a lot of different terminology. They all basically refer to the same things. Again, here, the same thing. We have the input variables and the and the output variables. We can also use the term the predictors and the target. Okay, so let's go through this a little bit quickly and then come back and go through it thoroughly. So here we are talking about how we're going to represent the predictors. We're going to use xi, and we're going to use cj for the classes. Now there's a little bit of confusion here, and that is as we change the I, in other words, if we talk about x1, x2, x3, x4, we're referring to a different variable, like maybe x1 is the outlook and x2 is the temperature, and so on. So as we scroll through the I's, we change the variable, but here for the class, as we scroll through this index, the J index, we're not scrolling through new variables, we're just scrolling through the values for that variable. So a little bit of confusion here in this kind of notation that I'm using. So for the golf playing example, x1, x2, x3, x4, they stand for these, but when we change C1, C2, C3, C4, we're not changing to new variables, we're just referring to the values play and not play. So we'd only have C1 and C2 in that case. And we saw that we could write the probability of one of the classes. For example, we talked about white chocolate or dark chocolate. So those are the different values for the class variable, and given values for the input variables or the predictor variables. So to classify the record, we compute its probability belonging to each class. So we say, given these are the inputs here. And let me just say that when we write the capitals, we're referring to the variables, but when we write small letters, we're referring to the values. So given a set of values for the variables, that's what we're really saying here. Given a set of values for the variable, we calculate C1, C2, as many different classes as there are. In the golf example, there's only 2 classes. And so we might calculate, given a set of values for these variables, the first 4, then what's the probability that they play, what's the probability that they don't play, and then we classify the record by choosing the outcome, which is most probable or most likely. Okay, one thing to notice, and that is that the above or the previous slide means that Bayes classifiers, this Bayes classification scheme, only works with categorical predictors. If we use a set of numeric predictors, then it would be very unlikely that any two instances that multiple records would have the same values for the predictors. So what that means is suppose that our input variables were not nominal, were not categorical, but were rather numeric. So suppose temperature wasn't measured the other way, but was measured as a number. Wind speed was measured as a number. Humidity was measured as a number. Suppose all the input variables were numeric. Then remember our scheme is, suppose we get a new record and the temperature was, 25.33 and the wind speed was 2.985 and humidity was 0.54557 or something like that, and the barometric pressure was something else, whatever. How likely is it that we're going to find an exact, remember the scheme that we're using is to find within our data set the exact, a set of exact matches for this, and then find out the class which is most prevalent for those exact matches. Well, we're not going to find any exact matches in this case, or it's extremely unlikely that we would find exact matches if the data is numeric, because there's far too much possible variation. And so it's very unlikely that we would find even one match in our data set for the instance which we're trying to classify, much less, if we would hope to find multiple instances and then choose the most likely or the most prevalent class within there. We won't even find one. So once again, note that the above means that Bayes classifiers work only with categorical predictors. It would be, if we use a set of numerical predictors, then it would be very unlikely that any two instances, that is multiple records, would have the same values for the predictors. Right? Therefore, numerical predictors should be binned. So what that means is, instead of using these raw numbers here, we should put these into categories. So we might say that if the temperature is between 10 and 15, that we'll call it cold, and 15 to 20 we'll call it medium, or something like that. So we're going to categorize the variables, and we call that binning. Okay, so let's actually try out the complete Bayes classifier, and let's make a even simpler data set just to make everything as simple as possible. So we're going to be talking about the golf data set, so we're going to have play and not play. But we're only going to have one input variable, one predictor variable, and it's going to be humidity, and it's only going to take two values, humid and not humid, or true and false, and we're going to set it up in this what we call a cross tab here. In other words, we're going to have a table like this. We're presenting it like this instead of as rows. Here we can see that there were a total of 1,000 people in the data set. And this 50 means what? It means that in the case of humidity, 50 people did not play and 180 people did play. And the total number of people that were involved when it was humid was the 50 plus the 180, which is the 230. And the total, and when it was not humid, there happened to be 770 people that were involved in that case, and 50 people did not play when it was not humid, and 720 people did play when it was not humid, and that gives us the 770. And if we want to look at it this way, we can see that altogether, regardless of the humidity or not humidity, there were 100 people who did not play and 900 people who did play. So just for practice, let's use 0R to decide how we should classify someone. So if we're using 0R, remember, or we also called it the naive rule. If we're using the naive rule or 0R, what do we do? Remember, we called it the benchmark. What do? We just choose the majority class, and we don't consider any predictor variables. So we don't consider humidity. So if we just consider the majority class between play and not play, there were 100 not plays and 900 plays. So in that case, we would predict that someone plays. So any new instance, we would say they're going to play. That would be 0R, or we also call that the naive rule. Okay, but here we want to try the complete Bayes rule or algorithm. So we will consider the variables, and in this case, though, we only have one input variable, one predictor variable, and that's the humidity. And it's either true or false, so it's either humid or not humid. We're going to predict play versus not play based on just one predictor, humid, not humid, or humidity, true, false. And so our input variable is just the humidity. And C is the class variable, and that can be either play or not play. And there are 1,000 records in this data set. And in data science, this set would be called the training data, because we're going to use it to build or train a model. So we're going to apply what's called the full classifier, or the exact classifier, or the complete Bayes classifier. So suppose now we have a new record to predict as to whether the group or the person will play or not play. And we want to use our training data to make the prediction. And we are going to use the information in the humidity variable. So we're going to know whether it's humid or not. If for the new record it's humid, then with the data which is shown up above, what would we predict? Well, if it's humid, then there are 50 cases where they don't play and 180 cases where they do play. So, of course, there are a lot more where they do play, so we would predict, given that it's humid, that they will play. So then the probability of not play, what is the probability of not play? Well, out of the 230, so it's 50 over 230. And the probability of play is 180 out of 230. So here we see where the probabilities arise that we decided we wanted to be able to calculate in order to choose the most probable class. And again, here we see the most probable class is play. So using the assign to the most probable class rule, we would say they will play. However, in this case, note that even if it's not humid, we're still going to have 50 out of 770 for not play and 720 out of 770 for play. So we're still going to predict play. So whether it's humid or not humid, we're going to predict play. And so that actually corresponds to what we would do with the naive rule, or what we call 0R. So the complete Bayes gives exactly the same prediction as the naive rule, or 0R. So actually in this case, the classification results are the same as if we were using the naive rule. So that was an example of using the complete Bayes, but on a very simplified data set. Okay, now we want to take a slight digression and discuss something called the Cutoff Probability Method. And then we'll come back to complete Bayes again. So let's suppose that we're running a very expensive golf course. And let's suppose that the operating costs are quite high, especially when this might be the daily costs. And when the course is open, the costs are much higher than when the course is closed. So we'll suppose that it's very expensive to run our golf course. Their electricity costs are very high. Employee pay is high. Insurance fees are high, and so on. So if it's going to rain and people won't show up, we feel it is better to shut down the golf course for that day to avoid all of these costs. And we don't want to take a chance of having the golf course open on a day when people are not going to show up. So we're not willing to make that kind of mistake. So the next 5 slides are a digression from our goal of explaining the Nalve Bayes theorem We will come back to that goal very shortly, though. So it may be the case that we are more interested in identifying instances of not play, and we don't care so much about misidentifying records that are play. So we just don't want to miss any instances of not play, and we don't really care if we miss instances of play. That is, we don't care if we call an instance of play not play, or we don't care as much as if we make the mistake of calling a not play instance a play instance. So we're choosing one kind of error is less important than the other, or one kind of error is more important than the other. So may be more important to identify not plays to us financially, because maybe if people will not play, we want to shut the golf course to save money. So we don't want to miss an example of suggesting that people are not going to play based on the weather, even if sometimes we will misclassify people who are going to play and we'll call it not play, but we're not as worried about that kind of error. Another example would be a case where we are classifying patients as having cancer or not based on some model that we have. Suppose we are more interested in identifying instances of cancer and don't care so much about misidentifying records that are not cancer. In other words, classifying a patient as having cancer when they actually are cancer-free. So we don't really mind doing that. What we really mind is calling someone who actually has cancer cancer-free. We don't want to do that. So we're more concerned with calling someone cancer-free when actually they have cancer, and less concerned about telling someone they have cancer when they actually don't. So both of those are errors. Let's just make that clear once more. So if we tell someone they are cancer-free when they actually have cancer, that's an error. On the other hand, if we tell someone they have cancer when they're actually cancer-free, that's also an error. So those are two different kinds of errors, and we prefer to make this kind rather than this kind. That is, we prefer to tell someone they have cancer when they don't, rather than telling someone that they don't have cancer when they do. So the idea is that we're going to establish a cutoff value for the probability of an instant being not play.